Okay, welcome back. So we're talking about number theory, and the last stuff that we talked about was modular arithmetic. So these are numbers that wrap around whenever you pick some number m to do modulo by after doing all your work. And we just noticed that we can save ourselves a little bit of work because, we're about to prove it, because we can do mod before we actually do those operations, before we do multiplication, before we do addition, and we'll actually end up with the same thing. Let's figure that out together. So really, all this, you could just do 77 mod 5 first, times it by 63 mod 5, so these numbers are super small now, between 0 and 4. Multiply those, then do mod 5. It's still the same answer, 1. So let me prove to you that you can do this, and it saves you a lot of time and effort and like space in your computer even. Let's prove it for addition. So we're going to prove the addition case, but we're also going to need some lemmas on the next slide. Just one really, but we got to work up to it. But in total, our theorem looks like this. It's like, well, you're trying to do x plus y. We're doing the addition case. Mod m. That's actually equal to, well, do it first. Do x mod m, make it small, then plus it with y mod m. And then you can do all of that mod m. It'll be very close, but you'll still have to squish it down sometimes. That's the idea. So that's the theorem. And that we're going to prove. So first we need a lemma on the next slide. So on to the lemmas. If we go and unravel the definition of mod, for any number x, it equals, well, some integer times m plus x mod m, okay, for some integer I. That is how you can divide x by m, okay? That's the point. And this gives a lot of neat facts. Like if I say 1 times 77 times 5 mod 5, this just goes away, because any multiple of the thing I'm modding by, it's useless. It becomes 0, right? It goes to 0. That's the entire point. So this is going to be just whatever was left. It's the 1. So that's some intuition behind this. Now let's use this to solve something. All right. So let's say x mod m. Well, that equals x minus im for some integer I. Don't know what it is, but this is true. Okay. If you try and divide x by m just using the definition of mod and the definition of like divides, you end up with this. And so we get this back. And we need this fact to prove our theorem. So how do we get there? Well, what is minus I but something negated? Let's say let k equals minus I. Then x mod m equals x plus km, because you can just replace k with negative I. Hey, I got what I wanted. So every time you do x mod m, it's really, there's some value that you can pick for k to make x that. Okay, so let's have a quick example, like, I don't know, 11 mod 5. So that equals 11. That's your x. And then, well, this is going to be eventually, right, just 1. So 11 minus, or I guess plus some negative thing, you can just bring it down to be between 0 and 4. Well, it's negative 2 times 5. Yeah, that is the answer. 1 on both sides. That is the point. So this is a useful fact, and we can use that now to prove our theorem. Let's do it. So, I think, if I remember correctly, it's easier to start with this side and then prove that it's equal to this. So let's do that. So we know we have x mod m and y mod m, and we can use this fact here. Once we know we have this, well, it's equal to the original x plus some integer k times m, most likely a negative integer. All right, so let's see here. X mod m equals x plus km. and y mod m equals y plus jm. And this is for some k and j, which are integers. We have that. Let's plug that in, because we have an equality right now. So let's see. Then x mod m. This is going to get a little messy. Let's see if we can do it on this slide. Y mod m equals, mod m after all that. This equals, if we plug in these definitions, this equals x plus km plus y plus jm mod m. Okay. Remember, our end goal is this. We need to get the x's and y's by themselves. Ooh, but we have some multiples of m's. Ho, ho, ho. This equals, well, x plus y plus m times, if I just factor this out and move them around, m times k plus j. Yeah? Mod m. And remember what I was saying about anytime you have an m multiple, and you're about to take mod m right after, that goes to 0. Okay, so then we have, finally, x plus y mod m for arbitrary x's and y's. Oh man, did we end up with this side that we wanted here? Okay, QED. So it's usually easier to take the mods first, then do your stuff. Do your multiplication, do your division. Or, sorry, do your multiplication, do your addition. That's the one. Only those two work with this. So, yeah, that worked out. I'm definitely not going to ask you to prove this on a test or anything like that, but it's very good to know because it helps when you're implementing things. It's very, very helpful when you're implementing stuff. That involves modulo at the very end. You can do it first. Okay, so take a second now to do this yourself. Compute the value of these following expressions and show your reasoning. 33 mod 7. So, probably the easiest thing to do for this one is just divide. Divide by 7. Show that 33 equals, well, 7, 14, 21, 28, right? 28, which is 7 times 4 plus 29, 30, 31, 32, 33, plus 5. Okay? And this right here is between 0 and 7 minus 1, so strictly less than 7. So that's a good remainder, and so therefore 33 mod 7 equals 5. Okay, just by using division, by using that and the definition of modulo / division. The negative one is interesting, though, so I want you to take a second to think about that one. Sometimes, and I should say this right now, some programming languages, wink wink C++, do this wrong. They don't give you back the mathematical definition when you use negative numbers. Some programming languages do not give back the mathematical definition of mod in this case. Sometimes they give back a negative remainder, in fact, and that's not what we want here. So, if we follow the real definition, we need to do this. We need to try and divide into negative 33. Okay, so negative 33 equals something times 7. So what's our something? Times 7, and then plus the remainder, which is our final answer. And that remainder must be between 0 and strictly less than 7. Yeah? So we might have to go a bit farther, because the remainder has to be positive. This is the one thing that can be negative here. So let's multiply by negative something. We have to pass 33. We have to pass negative 33. 7, 14, 20, and 28, 35. Let's go all the way down to 35. Okay? So This equals -5 times 7. And then we can have a remainder, because now we have -35. That can be positive. We can bring it back 2, yeah? That gives us -33. That's exactly what we wanted, and this can be our remainder, okay? So therefore, -33 mod 7 equals 2, okay? So positive number. That is the idea, and this one was 5. Okay, so I hope you got this one. This one's a bit complicated. Your programming languages sometimes don't do it right, but it's good to remember now. It has to be a positive remainder, okay, or a non-negative remainder, yeah? Okay, time for some more examples now. So another thing that I want you to try yourself is do all these giant things. Try them yourself. Obviously, you can put them into Racket and easily get the answer back. It might give you the wrong thing if you don't do the modulus first. If you use C++, because you might overflow and then things get weird, things like that. So try this. See if you can come up with a way to do this yourself without using a calculator even, because there is a way. Otherwise, you can just plug it into Racket on a test or something, right? Okay, 44 to the power of 12 mod 6, and the answer is, the idea is, this is just a bunch of multiplication, so we can shrink this thing down, mod 6. Okay, so 44 mod 6. This equals 44 mod 6 to the power of 12 mod 6. And what in the world is this right here? I don't remember off the top of my head. If I tried long enough, I could, but let's just go to Racket. Modulo. What was it? 44 and 6. Okay, it's 2. So now it's 2 to the 12 mod 6. And this is where you can do tricky things that I don't expect you to know, but it's fun to show you that you don't have to use a calculator. Technically, I didn't have to use one here, but I didn't want to think too hard. So 2 to the 12 is, well, it's just 2 to the 6 twice. Bam. Do all that mod 6. Okay. These are both, what? 2, 4, 8, 16, 32, 64. You'll get good at that as a computer scientist. 64 times 64. Dun dun dun. Mod 6. And what is 60? Then we can finally use this silly theorem that we proved. It's useful now. It's no longer silly. What is 64 mod 6? Because we can just do that first and then take the mod 6 later. Well, 60 is the closest multiple of 6, so it's 4, yeah? Equals 4 times 4 mod 6. Because 64 mod 6 is just 4, right? Yeah. Which is 16 mod 6. Which equals 12, and then there's 4 left. Equals 4. Isn't that nice? Let's see if I made a mistake. Is it expt 44, 12. Hey, very, very nice. All right, now you try this one with this in mind, okay? If you didn't already. And the answer is, okay, well, 5 mod 7 is already how we want it to be, so let's figure this out. So I guess one thing that you can do is, this is 25 3 times. Why not? 25 times 25 times 25 mod 7. Bam. Okay, let's break down the 25 because we mod 7 that. 7, 14, 21, so that's 4. 4 left over. 4 times 4 times 4 mod 7. Hey, hey. And what do you know? 4, 16, 64, isn't it? 64 mod 7. Which is quite close to 70, but not yet there. It's let's see, you can get to 63, and then there's 1 left over, right? So it's 1. Okay, you see how we didn't need a calculator for that? Let's confirm that I'm not telling you the wrong thing. 5 to the 6 mod 7. Hey! Alright, I'm proud of myself. Okay, so that is modular arithmetic, and we are making good use of those theorems because we can break down these numbers by using mod. And then we can do our multiplication that makes larger numbers. Okay, so we can start with smaller numbers before we make them big again, is the idea. Okay, so now we're ready for some more number theory. And this will come back to modular arithmetic. I promise. It's weird, but it does. Let's talk about primes. So a number is prime if it is an integer greater than 1, so 2 onward has the possibility of being prime, and its only factors, so the things that divide it cleanly, are 1 and p. So you know how to check for division in like C++ or something? So like if you check for division by, check for divisibility by 2, you say something like x mod 2, check that it's 0. That's how you check for divisibility, check for a factor of 2, right? So just remember that. A positive integer, we say it's composite if it has a factor other than 1 or itself. I'm sure you remember all these silly definitions from some math class once upon a time. And we have these as well. So let's go back to them. The greatest common divisor of non-zero integers, x and y, is the largest positive integer that is a factor of both x and y. That's an interesting fact. So let's have some examples here. Let's say if I had, I don't know, 12 and 18. Well, 12 is 2 times 3, and 18 is 2 times 3 times 3, right? And so they share what in common? A 2 and a 3, right? So 6 is the greatest common divisor. So 6 is the GCD of 12 and 18. And similarly, you have a least common multiple. It's the dual of this, if you remember that word from the beginning of class, in a very precise sense of GCD. So the least common multiple of two non-zero integers, x and y, is the smallest positive integer. See, largest, smallest. That is an integer multiple, see, factor multiple of both x and y. Okay, so it's something bigger than it usually. Dun, 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 if they're both positive numbers. So let's find the least common multiple now of not 12 and 18, but let's see. I don't know. 6 and 8? Let's try that. Let's try 6 and 8. So it's the smallest thing that they both share. So for 6, you can go 6, 12, 18, 8 goes 16, 24. Ooh, 24. Okay, so 24 is the least common multiple of 6 and 8. It's the smallest thing that they both share in common when you just start counting by 6s or counting by 8s. Yeah? That is the idea of least common multiple. And then finally, we have relative primeness. So if the greatest common divisor, the GCD of two numbers, is 1 itself, numbers are relatively prime to one another. Okay, so they share no factors other than 1. I don't even know if 1 counts as a factor. That's the point. So obviously, any number and a prime number that isn't a multiple of it, they're all relative prime. Okay, so something like, I don't know, 7 and, let's see here, any two primes are relatively prime, of course. Well, let me come up with a better example. 7 and 12, for example, are relatively prime because 7 is just 7, and then 12 is 2 times 2 times 3. They share no factors. 7 and 12 are relatively prime, and then any two primes are, of course, relatively prime. But 12 itself is not itself prime, okay? Maybe I should say that. That's the key. Not itself prime. It's just when it's in a pair with some other number, and the GCD is 1, it's called relatively prime. Okay, so that is what it means to be relatively prime for two numbers. And now I have the wonderful opportunity to teach you one of the coolest theorems on the planet. So there are an infinite number of primes. Are you ready? We now know the definition, so I think it's time. I'm going to prove to you with beyond a shadow of a doubt that there are an infinite number of prime numbers. Okay? That is the hope. So let's do this. And the intuition is based on this. 2 times 3 times 4 times 5, just a bunch of numbers, starting at 2, wink wink, plus 1, it's actually divisible, or is it not? Like, the question is this divisible by any of those original numbers, 2, 3, 4, and 5? If you multiply them together and then get 1, is it divisible by any of those original numbers? That is the question. And just to drive the point home, maybe I should make this 5 and 7. Yeah, 5 and 7, which are primes. Ho-ho. So is this number, whatever it is, divisible by any of 2, 3, 5, or 6? There, sorry, 5 and 7. Let's find out. Times 2, 3, 5, 7, and then add 1. That is 211, apparently. Do any of those numbers go in cleanly after adding 1 to this original number? Let's see. Well, 2 can't go into it cleanly. No, sorry. Got it backwards. 2 can't go into it cleanly because we just made sure that it is that it's odd, because multiplied by 2 you get an even number, add 1 you get an odd number, so 2 is unhappy. 3 is unhappy for the same reason. So it went in by 3 cleanly, but we added 1, so now it's going to be mod 1. 5, mod 1. Ooh, 7, mod 1. It doesn't go into any of those original numbers after we added 1. Oh, no, I wanted to circle it. Bam. That's the intuition. So now let me show you the proof. So there are an infinite number of primes. We're going to prove it by contradiction. So let's assume the theorem is false. And in our proof, we're going to use the fact that every number is a multiple of its prime factors. That's an obvious thing. Okay, so proof, let's do this. By contradiction, so assume there are a finite number of primes. And you can list them all. Finite number of primes. So that means you can list them, you can write them all down if you had enough time. Maybe there's a large number, but there's a finite number. I'm going to rewrite that because that looks horrible, even by my standards. There are a finite number of primes. That's a number sign. Assume that. Okay, so we can list them all. There's, I don't know, there's P1, P2, P3, all the way down to Pn. There's a listable number of them. And they stop. Pn is the last one. The last prime. Okay, that's fine. Now, let's make this number. P1 times P2 times P3. Let's say consider. Consider P1 times P2 times P3 times ... all the way to times Pn, and then add 1. You know where I'm going with this. Consider that number with an R. Well, we need to be able to specify this number. Every number, it's a multiple of its prime factors. It better be a multiple of all these primes, because those are all the ones that exist. It must be a multiple. There's some expression involving all those things, right? It must be a bunch of the primes multiplied together in the list. Primes P1 through Pn multiplied together. Because every number is a multiple of its prime factors, and this is all the primes that exist in the world. So this number that we just made better be a bunch of these primes multiplied together. Yeah? And the kicker is, nope, not at all is that true. But none of P1 through ... Pn divide into this number? Consider, I don't know, let's call it k. Divide k. By construction, they don't divide k. What? That means, every number must be a multiple of prime factors. We know that's true. That means, so, either k itself is prime, which is a possibility, because there must be something like that wasn't in our list that was prime. So either k is prime, or there's a prime in our list that it is a factor of that is not listed in it. Okay? There is a prime that isn't k. K is not prime. But there is a prime that we forgot. Okay, I hope you see that these are your two cases. Either k is prime or it's composite. But still, if it's made of prime factors, it's missing one, because obviously none of ours went into it. So, that's a contradiction. Exclamation point. QED. Okay, I hope you see that. So we said that we listed all the primes, but no matter what, we're going to find a new prime somehow, without listing it, that wasn't in our list. So that means our list wasn't complete, which means there was not a finite number of primes. So our assumption was false. We proved false from it. We derived a contradiction. QED, there are an infinite number of primes. Wasn't that cool? So that is a fun little proof that I am happy to be the one to teach to you. Okay. So let's move on right now to combine primes and modular arithmetic. Okay, it's coming together. Primes plus modular arithmetic equals love. Okay, here's a theorem, a fun one, due to Fermat. So if p is prime, a is an integer, and a is not divisible by p. I know this is a long list of side conditions. A to the p minus 1 is equivalent to 1, congruent to 1 mod p. Isn't that weird? How odd. How odd. Let me prove this to you for p equals 5 and a equals 2. So first of all, 2 to the 4 equals 2, 4, 8, 16. But mod p, which is 5, what is that? Yeah, that's right, it's 1. And my hand-wavy proof to you, I'm not going to prove this to you, you can look it up on Wikipedia if you'd like. It's a bit more complicated than we have time for. My hand-wavy proof to you is that multiples of a is the number itself, I don't know. Maybe it's hard to read. Maybe I should put this in bold. Multiples of a, the number a, this variable right here. Yeah. Come on. There we go. That a. Multiples of that a, they cycle through every non-zero element of CP. So all the numbers, remember this is all the numbers between 0 and 1 all the way to p minus 1. That's CP. And we're saying we're forgetting about the 0. So it cycles through every non-zero element of p. Let's try this for, let's see here. Let's try it for a equals 2. So 2 to the 0 mod 5. Let's make sure I'm still recording. Yes. 2 to the 0 mod 5 equals, well, that's just 1, right? Then 2 to the 1 mod 5. I'm just going to drop the mod 5. 2 to the 1 is equivalent to, that's just 2. 2 to the 2 is equivalent to, congruent to 4. 2 to the 3, 2, 4, 8. That goes in 3 times. Ooh, you see the pattern? And then 2 to the 4 mod 5 is equivalent to 1 again. You see that? So it goes through 1, 2, 2, 3, and 4, and I didn't really need the 0. That was, I guess, where it started, right? That one doesn't really count. Maybe we can erase that. It wasn't really necessary. But it does wrap around is the idea. So you see how it's going to do that, and it's going to keep going because, I mean, it's just back at where it started. So it's again at 1. So if you multiply this by 2 on both sides, of course you're going to get back 2 next. Things like that. So that is my hand-wavy proof to you, and the last part of it is, okay, so the only way for a cycle to restart is to get to 1 eventually, because then you have to multiply once more on both sides, of course, and then you'll get to your original a again, which was 2. Okay, so that's how you start at 2. That was my hand-wavy proof to you. That's why it has to be that the p minus 1th element of this cycle is always 1. Okay? And oops, I think this was a remnant of when I was designing this slide. I was going to try and teach you a more general thing first. So this is the theorem. Okay? So that's all I wanted to show you there. And now we are ready for one of the most important theorems of this class. It is called the GCD Theorem. It's going to come in so much use when we do RSA. Oh man, is it a great theorem. So I'm going to try my best to explain it to you. Let's do this. So here's the theorem. Let x and y be 2 positive integers. Let's make sure I'm recording, yes. Then the GCD of x and y is equal to the GCD of y mod x and x, which is interesting because this is a smaller number. What? So like the GCD of these 2 big numbers is the GCD of one of those same numbers, and then a smaller version of the number. Oh man, this can eventually get tiny and lead us to the answer very quickly. Hey. So we're going to prove this theorem, and we're going to prove it in a different way. We're going to prove this real theorem down here. So what we're going to do is instead prove that every factor of x and y, so if you have 2 numbers, x and y, every factor of x and y is also a factor of y mod x and x. Okay, you see that? So that is the idea. And if we have this theorem and it works, if that's true, then obviously, if they share every factor, they're going to share the greatest factor / divisor. Okay? Because factor is the same as divisor. Yes? Hey. That is the hope. Okay. So, this is the real theorem. For all factors f, numbers x and y, if f is a factor of x, so f divides x and f divides y, that is true if and only if, in both directions, f divides y mod x and f divides x. Okay, so that's the theorem. And remember that this is 2 things at once. It's this way, with implication, and then also reverse it in implication as well. So it's both of those. And so if we want to prove this theorem, we have to prove both ways. We've got to prove like A implies B, and then B implies A, like that. Okay, so remember that is equivalent to B implies A. Gotcha? Okay, so that's what we're going to prove. So let's do the left to right direction first. So we're going to assume the left side, prove, oops, no, thank you, oops. Assume the left side and prove the right side. Okay, prove this side over here. That's what we're going to do. Are you ready? So we're assuming this stuff, and we're going to prove this stuff. Okay, so, well, assume this. F divides x and f divides y. Okay, then we're going to prove that f divides y mod x and f divides x. So we actually naturally get f divides x quite simply from this by assumption. F divides x. That's not too bad. Now we just have to prove this fact right here. F divides y mod x. How does it do that? Okay, so remember something that we proved up here, one of our little lemmas. Anything that looks like this is equal to x plus km for some integer k. We're going to use that to our advantage here, okay? It's not going to make sense until we finish it, but I promise that's the right thing to do. So y mod x equals, what is it? Dun dun dun. equals y plus kx. Okay, that's hard to remember. Y plus kx for some k. Okay, okay. We know this. We know this. We know this. What is this? What is this number right here? Does it look like any of the definitions we know? Does it now? Well, what if I put it this way? What if I say y mod x equals y plus kx equals 1 times y plus k times x? What is that? What's the definition? That should be coming to your mind. Where is it? Way up here somewhere. Hey, that's a linear combination. That's a linear combination of x and y, isn't it? Oh, what does that mean? We proved a theorem about that. If x divides two different numbers, then it divides any linear combination of those numbers. Ooh, 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 ooh. Yes, yes, yes. Therefore, by our theorem above, it's a linear combination of x and y. Therefore, dun dun dun, f divides, dun dun dun, y mod x. Isn't that fun? Isn't that nice? It's just a product of this theorem right here, because y mod x just so happened to be a linear combination of two numbers. We knew that f divided y, f divided x, so f divides any linear combination of x and y. That's super nice. That proves this side. Okay, so that's like half QED, like an unfilled box. Okay, now we're ready for the right to left direction. So we're going to assume the right-hand side, this over here, and then prove this side right here. Okay. So let's assume these things are true, and then we're going to go and prove this stuff right here. Are you ready? Let's do this. So assume f divides y mod x and f divides x. Sure. Let's use that definition from last time again. Well, y mod x, that must be y plus kx for some k. Y plus kx for some k. Now remember what we're assuming. F divides this number and this number. And again, we're going to use that fact that it can divide any linear combination of those numbers. Hey, hey, hey. Okay. I guess one thing that we need to prove is f divides x again. So by assumption, we have that again. It's just the hard work is proving f divides y now. That's the key. Okay, so let's do this. Let us do this. So y mod x equals that. Can we solve this for y? Dun dun dun. Y mod x, all this stuff right here. Solve that for y. Because that's what we wanted. We wanted to find a way to make y. So y equals y mod x plus kx. And what do you know? 1 times that plus that is another linear combination. This is crazy. Of y mod x this time. That's one side. And x. Therefore, by this theorem way up here, that we didn't know what we were doing it for, oh man, does f divide y. because we had f divides this thing, f divides this thing. We found out that y is a linear combination of these two things, y mod x and x. So we know immediately by this theorem that dun 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 f divides y itself. So we can make y a linear combination. That's the craziest thing, man. QED. So now we know that the GCD of x and y is equal to the GCD of y mod x and x. And when you put that together, you get this wonderful thing called the Euclidean algorithm. Okay? If you keep on replacing GCD of x and y with the GCD of y mod x and x, eventually you're going to get back GCD of 0 and that number. Okay? And because everything divides 0, like, I don't know, 1 divides 0, 2 divides 0, 3 divides 0, dot, 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 dot. It's not 0 that's weighing you down, it's z at this point. And the greatest common divisor of z, if it had to pick, it's just z itself. You can't go z plus 1. It's not divisible anymore. So z is the biggest divisor of both 0 and z. So the GCD of 0 and z is just that z, and that happens to be the GCD of those original x's and y's. What? That is the Euclidean algorithm. Okay? And that is where I want to stop today. This is what you're going to start implementing in your lab. So this is very important for you to have seen it here. Now you know exactly why this works. But you're going to implement the GCD in this way. You're just going to keep on replacing xy with y mod x and x until you get the x side, the left side being 0, in which case you're done because the right side is your answer. Okay? You have done it. You have survived my lecture on the Euclidean algorithm. It took a while to get here. It took some weird looking proofs. But if you followed that, oh man, is this satisfying. Okay? We can find the greatest common divisor of any two numbers very, very efficiently. Okay? That's the Euclidean algorithm invented by Euclid, who lived quite a long time ago. This is a very old algorithm. Okay? So that's where I want to leave you, and I will see you now in your lab. So I'll see you then.